Hello friends, in this video I'd like to solve the following problem from the Ibero-American Olympiad for University Students 2017, problem number 4. We wish to find all functions f from the set of real numbers into itself such that the following two conditions are met, namely f of x plus y equals f of x times f of y, and f of x should be greater than or equal 1 plus x for all real numbers x and y. So my hints for this problem are the following. First of all, the key to this problem is Cauchy functional equation. Recall the following fact, that if some function g satisfies Cauchy functional equation, that is g of x plus y equals g of x plus g of y, and furthermore, one not rather strong, it's rather weak condition, if g is bounded from below or from above on some at least one non-empty open interval, then function g must be linear. So in other words, g of x equals a times x for some constant a. So the basic idea is to reduce our problem to some kind of Cauchy functional equation. To do that, think about what happens if f, our function, has a 0. Then try taking natural log on both sides of our functional equation. And at some point, you may want to investigate the behavior of the following function. You will see in the process. So give this problem a try and I will see you in a minute. Okay, so my solution will be the following. First of all, let's consider what happens if first case, let's say, case number 1, if f of, let's say, y0 equals 0 for some y0 which is real. What happens then? Then let's set x to be really any value and let y be equal y0. We have the following. F of x plus y0 equals, well, 0 because f of y0 is 0. In other words, x was arbitrary, so our function is constantly 0. Our function is constantly 0. Can it happen? No, it can't, because it's against the condition which I marked double asterisk. Contrary to condition double asterisk. Okay. So let's consider second case, case number 2. Case number 2, when f of x is non-zero for every real number x. Okay, what happens now? Well, now let's set y to be equal x, and our functional equation becomes f of 2x equals f of x squared. Since f of x is non-zero, this is positive, so our function is positive. So, in other words, for every real number x, f of x is positive. And that means then we can take natural log on both sides of our functional equation. So, let's take natural log on both sides of our condition which I marked asterisk. What happens now? Well, we have the following. Natural log of f of x plus y equals natural log of f of x plus natural log of g of x. Because remember that natural log of a product is sum of natural logarithms. And then let's make a nice substitution. Let g of x be equal natural log of f of x for every real number x. Notice that we have just Cauchy functional equation. G of x plus y equals g of x plus g of y. And moreover, so it's from our condition 1 asterisk. And from our second condition, double asterisk, we get the following. After taking, let's see, after taking double asterisk and taking natural log on both sides, we will have g of x is greater than or equal natural log of 1 plus x. Of course, this only works for x's which are greater than minus 1. Okay, but let's notice the following. That implies that g of x, g of x is greater than 0 for x's which are from 0 to infinity. Very important, very rather trivial, but very important. So in other words, our function g satisfies Cauchy functional equation, and moreover, it's bounded from below on this interval. And that suffices to state that means that, well, g of x must be equal, let's say, c times x, or some constant c. And let's go back because g of x was natural log of f of x. So natural log of f of x equals c times x. And taking exponential function, that means that our function must be of the following form: e to the power some constant times c. So now we know very much about our function. Our condition 1 asterisk is satisfied. So now let's investigate our condition double asterisk, which says that the following should be satisfied: that e to the power cx should be greater than or equal 1 plus x for every real number x. The question is, for what values of constant c is this satisfied for every real number x? So first, I will consider two cases separately. Case number one, well, if x is less than or equal minus 1, then, well, for every constant c, e to the power c times x is obviously greater than or equal 1 plus x. Why is that? Because this number is positive and this number is non-positive. So nothing is interesting in this case. Case number 2. If x is strictly greater than minus 1. What can we do? Well, we can take natural log on both sides. So you know what? I will mark this double asterisk. So double asterisk becomes what exactly? C times x should be greater than or equal natural log of 1 plus x. And then now we have two subcases. I want to divide by x, but I can't without further assumption. So I have subcases. Case 2.1 If my x's are from -1 to 0, then the following should be satisfied, namely c is less than natural log of 1 plus x over x. Case 2.2, if x's are positive numbers, then we divide by x and c should be greater than or equal this. What happens if x equals 0? Well, if x equals 0, on the left hand side we have 0, and on the right hand side we have 0 as well, so nothing special. So my idea is now to investigate this function near 0. Near 0. So investigate, let's call this function h of x, which is natural log of 1 plus x over x near x equals 0. Okay, so let's do exactly that. So I want to, first of all, I want to find the limit. Find the limit as x goes to 1 of h of x. If x goes to 1, not 1, but to 0, sorry. Limit as x goes to 0, natural log of 1 plus x over x. I have indeterminate symbol 0 over 0, so I can use de L'Hopital's rule. By de L'Hopital's rule, derivative of the numerator is 1 over 1 plus x. Here we have 1, so our limit is just 1. So we know that our function gets closer and closer to 1 at 0. And moreover, I want to find the derivative of my function. So let's investigate the derivative, h prime of x. Well, h prime of x, I have x squared in the denominator. Here I have x over 1 plus x. And here I have minus natural log of 1 plus x. Very well. And now I will write it maybe in this form, x squared 1 plus x. And here I have x minus 1 plus x natural log of 1 plus x. And, well, what can we do? I want to investigate the sign of this expression near 0. And let's take a look. If x is between -1 and 0, well, the denominator is always positive, so nothing special here. But let's take a look at the numerator. So I have this, and this is negative. This part right here is positive, obviously, and this part is negative. So nothing obvious for now. So to find the sign, I will consider one auxiliary function. Let's call it k of x. K of x, or maybe let's call k of x equals x minus 1 plus x natural log of 1 plus x, and I will investigate this function for now. So let's differentiate it. I have 1 minus natural log of 1 plus x minus 1 after differentiation, after using product rule, and it is minus natural log of 1 plus x. Yes, it is. And that means that our function, we see that this k prime of x is negative if x's are where if x is greater than 0, our derivative is negative, and if x's are from -1 to 0, from -1 to 0, I have a positive derivative, which means that k increases on -1, 0 and decreases on 0, infinity. So k attains its maximum. K attains its maximum at 0. Its maximum at x equals 0. And what is this maximum? Well, if I plug k of 0, I have just 0. K of 0 equals 0. And remember, this is the maximum of my function. So that implies that h of x, my previous function, or rather h prime of x, is negative for x's from -1 to 0 union 0 infinity. Once again, why is that? Well, because we know that k of x was just the numerator of my function. It was just the numerator. And I know that my numerator is negative and attains its maximum, which is 0, only at 0. So for every other x, my derivative is negative. So my function h is decreasing. H is decreasing on -1 infinity. Okay, so my function is decreasing, and I need a new page. Okay. What does it mean? Well, now we can more or less visualize the graph of h near 0. Near 0, if I have my axis here, x, y. Well, I know that my function near 0 equals 1, at 0 equals 1, and it's decreasing. So here I have 1, and it goes something like that. That's part of my graph of y equals like h of x. Okay, and remember, let's go back a step. Remember that this should be satisfied. I will copy it. This should be satisfied. So let's take a look at our graph. If we are near 0 from the left-hand side, my c should be less than or equal, well, any number greater than 1. So from that and from our graph, we get that c must be less than or equal 1. But from the second case, c must be greater than or equal every number slightly less than 1. So c at the same time must be greater than or equal 1. Greater than or equal 1. And that can mean only one thing. That means that c equals 1. So in other words, only one function can possibly satisfy our functional equation. Only one function can satisfy, well, our functional inequality, which was marked double asterisk, namely f of x equals e to the power of x. The only question now is it really satisfied? Is it really? Yes, it is, because notice that our condition double asterisk was in fact equivalent to these two inequalities, conjunction of these two inequalities. This one should hold for these numbers, this one should hold for these numbers. And obviously, if c equals 1, both of them are satisfied. So now we know that, in fact, our functional equation and functional inequality have only one solution. The only solution f of x is e to the power of x. And that closes our problem. Before you go, by the way, this inequality, namely that for every x, real x, e to the power of x is greater than or equal 1 plus x, has a special name. You probably recognize this name. It's so-called Bernoulli's inequality. So we have just demonstrated that among exponential functions, only one function satisfies this type of inequality, namely e to the power of x. For example, 2 to the power of x fails to satisfy this inequality at some real x. So by the way, this inequality is called Bernoulli's inequality. It's very famous in mathematical analysis. It's sometimes useful when dealing with definitions of real powers, for example. When defining real powers, Bernoulli's inequality is rather handy. And that is it. So thank you for watching, and I will see you next time. Goodbye.